So the first part that we learned was basically how to expected value and standard deviation, which is width, and we understand where the shape is, and spread. Now we have a very cool rule, and we're going to be using this more in the next unit as well, and that is when the distribution is mound-shaped, like the center one that we had, and symmetric. About 95% of the data are within 2 standard deviations of the mean. So what does that mean? Well, if mu is here, if I go this far, 2 sigma, so that would be mu plus 2 sigma. Some people said, is that 20? No, that's a sigma. And if I go to the left 2 sigma, that would be mu minus 2 sigma. Sigma, not 20. Then I would have about 95%. By the way, they should be equal length. 95% of my data will be right in here. Usually, if anything is outside of that, we say that's unusual. So over here is unusual, and over here is unusual. All right? So let's go ahead and look at one more example. A student rolls a 4-sided die 100 times and counts the number of times they roll a 1. What is the expected value and standard deviation for the number of times you get a 1? Well, before, the nice thing about the formula we learned is before, in the old days, we'd do a table. Do you remember that? And I go, okay, x is 0. Let me find the probability of getting 0, which, by the way, n is 100. P would be, it's 1 out of 4, so it's 0.25. So Q is 1 minus 0.25, which is 0.75. And I could do a table and have this all the way down to 100, right? Calculate the probabilities, which would be a real pain, by the way. 0.25. And then you'd have like 90. Don't even worry how I'm doing this over here. This is a real mess, all right? So you'd be doing all that. But the nice part is we can just use these formulas. The mu is just n times p. Before, we'd have to like multiply all these out and add them up. But I'm going to get the same answer if I just do this. So I expect 25 ones, which on a 4-sided die, that makes sense. The harder part is the standard deviation, because that's where we really needed the calculator. But luckily, we have this nice, beautiful formula, square root of npq, square root of 100 times 0.25 times 0.75 square root, or about 4.33. So this is my spread. So what does that mean? So let me draw a rough distribution. Sorry, I chopped that off. I didn't realize that. We got 0 to 100. Most of my ones, most of the time I'm going to get about 25 ones. So here's 50, here's 25 roughly. So my peak's going to be right here. And where most of my data on the left, I'll have most of my data points 2 standard deviations below that. So what is 2 sigma? 2 sigma in this case would be 2 times 4.33, or about 8.66. So on the left side, if I go 25 minus 8.66, I get 17.34. So that's maybe around there. Most of my data over here is going to be in that section for that half, right? And then 2 sigma to the right, add 25 plus 8.66. Here's by the way, 17.34. And I'm going to get 33.66, which is probably around here. Most of my data will be here. And then I'll have a little bit, 5%, split between these two. So 2.5% here, roughly. Again, not exactly perfect, but roughly. So if I asked you the question, would it be unusual, let me write it, 33.66, to roll a 1 40 times out of 100? Well, before I told you this rule with this window right here, you said, well, it's definitely higher than 25, but is it really high? We can tell here that it's 40s around here. So that would definitely be, this is unusual over here, and it's unusual over here. Spell? All right, so yes, it is more than 2 standard deviations. Away from the mean. So it's definitely unusual. All right. Now you suspect the die is loaded and that you're getting too many ones. How many ones would you have to roll out of 100 to say, hey, I'm getting too many ones? Obviously 26 is not that unusual if you expect 25. Well, we can use our graph again. Look at this number. So for this question, we could say 34 because anything above 34 or higher, because anything above 33.66 is unusual. If I wanted to say, hey, maybe it's loaded, so I have what would be an unusually small number of ones, unusually small, so this is another example. Unusually small, usually small, would be 17 or lower, because it's on this side, because it is more than 2 standard deviations below. So the main thing you learn on this part of the lesson is how to determine if something is unusual below mean.